This is the beginning of part 2 of our module on credit-linked notes. We remind you that this part 2 contains a single chapter, chapter 2, which introduces basket CLNs, i.e. CLNs that refer to a basket of credits rather than to a single credit, and also teaches you how to evaluate the risk-return parameters of this instrument and some of its relevant accounting and regulatory treatment. The simplest form of basket CLN is one that refers to two reference entities instead of just one, and specifies that if either of the two reference entities experiences a credit event, the note is extinguished and the issuer delivers to the holder a defaulted obligation of that reference entity. More typically, basket CLNs make reference to some 4 to 10 reference entities and can be structured to pass on to the note holder the risk of default of the first reference entity that experiences a credit event, or the first two, or perhaps only the third one but not the first two, and so on. Hence the more generic nth to default label to describe these instruments. Our analysis of the correct pricing of these instruments is focused initially on the simple version we began with, namely a first to default out of two only, because we can develop for this version an Excel-based pricing model that requires only the most basic mathematics. As soon as the number of reference entities reaches 3 or more, the mathematical complexity increases significantly, although the insights we can develop from our simple example continue to apply. It should be evident that the pricing of the note we have described will include among its inputs the individual default probabilities of each reference entity and of the issuer, and the expected recovery value of each following a credit event. It should also not surprise you that the default correlation between the two reference entities and between each one and the issuer will play a key role in the valuation process. To simplify our task, we assume the issuer is an excellent credit whose default risk we can ignore, which means we can also generally ignore the default correlation between the issuer and the two reference entities. This leaves us to contend with the default correlation of the two reference entities, which we definitely cannot ignore, particularly since some of the most popular basket CLNs often contain 5 or 6 credits from the same industry, such as banking or autos. We said earlier that where two entities, A and B, are independent, their joint default probability would be the multiplication of their individual probabilities of default. Where they are not independent, this formula needs to be adjusted to read as follows. Note here, the joint default probability of A and B equals the multiplication of their individual probabilities of default exactly as before, but then we must add the item in the last line you see here, which includes the correlation A and B term multiplied by two terms, both of which have a square root sign above them. And then this formula, correlation AB, is the default correlation between entities A and B, and PS in U term of an entity K is the survival probability of K, so equals 1 minus the default probability of K. We have argued previously and in earlier modules that the estimation of default correlation is phenomenally complex, and therefore have left this topic to a later dedicated module. But we do know for certain that, like any correlation, it must be a number between +1 and -1, and at least in the view of our company, DNA Training and Consulting, default correlation cannot often be negative given how many common factors affect all companies and entities in the world. And this is true, in our opinion, even for two companies that have admittedly inverse exposures to one single risk factor or a handful of risk factors, such as the exposure of airlines and oil producers to the price of crude, or the exposure of insurance companies and construction companies to a devastating hurricane. We will therefore assume for our purposes, as mentioned in the previous bullet point, that default correlation always lies between 0 and +1. With these observations out of the way, we are ready to develop a complete pricing model for our basket CLN. Returning to our diagram from earlier, you will see that we have added a large rectangle around the two overlapping circles and have colored each area within the diagram in a different color. The overlapping area in red represents the case in which both entities default, whose probability is therefore provided by the formula immediately above. The light green moon-shaped area on the left represents the case in which A defaults but B does not, since we are not in the red area. The probability of this scenario is quite simply PD of A minus the joint default probability. After all, it's the entire circle on the left minus the common area. The blue moon-shaped area to the right represents, by symmetry, the case in which B defaults but A does not, and therefore the probability of this scenario is quite simply PD, default probability of B, minus the joint default probability. And finally, the area beyond the boundaries of the two circles, but still inside the rectangle, which is colored in light yellow, represents the case in which neither A nor B defaults. Since we know that the sum of the red, light green, blue, and yellow areas must add up to 1, being all of the possible states of this pair of entities, we can write, therefore, probability of default of neither, i.e. the probability they both survive, is 1 minus each of the previously calculated amounts. We can therefore define entirely the probability distribution of outcomes and build an Excel spreadsheet for this. This worksheet 2RE PDF, which stands for Two Reference Entity Probability Distribution Function, requires inputs of the individual default probabilities for reference entities A and B, which we will assume initially are 2% for each, and the default correlation between them, which will appear in this row 6. A 1-year tenor is assumed for the rest of this module. The worksheet then calculates the probability for each of the 4 scenarios we outlined a minute ago by use of our formulas, which are programmed in rows 7, 8, 9, and 10. Just to illustrate, here is the long and complex formula for the joint default probability of A and B. Here is the formula for A but not B defaulting. Remember, it is the subtraction of one item from the other. The same for B but not A defaulting. And finally, for neither of them defaulting, you may recall, using the rectangle example, we said it would be 1 minus the sum of the previous 3 items. Most of the results you see on this worksheet should not be surprising. We summarize them next. First, at low default correlations, the probability that both reference entities jointly default, shown here, is far smaller than the individual default probability of 2%. Second, as default correlation increases, it becomes more likely that both reference entities default, which really is the same reason behind the old proverb, do not put all your eggs in one basket. Note in particular that at a default correlation of 100%, the joint default probability becomes 2% exactly, which equals, not surprisingly, the individual default probabilities of 2%, since at that point with correlation of 100%, the 2 reference entities are essentially identical from a credit risk perspective. In a sense, they live together or die together. Third observation, if we raise the individual default probabilities significantly, for example to 20%, we start seeing a substantial likelihood of a joint default, and especially so, of course, for high correlation levels. Note finally row 11, which calculates the probability that at least one reference entity defaults, and is obtained simply by summing the rows 7, 8, and 9 as shown here. The need for this row will become clear in just a moment. Graphics are especially helpful to visualize the effect of rising default probabilities and correlations on the various scenarios. This worksheet, labeled Graphics Low PD, reproduces at the bottom a rectangle containing the 2 overlapping circles for correlations assumed to be 0% in the first case, 40% in the second case, and 80% in the last case, while default probability is held at 2% for now. The low individual default probability of 2% is represented at the bottom in the rectangle by the relatively small size of each circle. In reality, of course, these circles would have to be even smaller than they appear here, since they would need to be individually only 2% in size of the total rectangle. But that was not so easy for us to do graphically. As we increase default correlation and move to the right in the worksheet, the overlapping area that you see at the bottom in the rectangles between those two circles increases. That is the area in red getting larger, which of course causes the total area covered by those two circles in fact to become smaller. At a default correlation of 80%, as shown in this last diagram on the right here, the two circles overlap almost completely, and ultimately at a 100% default correlation, which we have not shown, they would become identical. And in that scenario, we would be left with only two possibilities instead of four. The yellow area representing the case where neither reference entity defaults, and then the red area representing the scenario where they both default and there would be nothing in between. This next worksheet, labeled Graphics High PD, depicts the same scenarios as the previous one, except for the adjustment of the individual default probability to 20%. The circles at the bottom have therefore become larger, significantly larger than before, so that the overlapping area is significantly larger as well than before, and becomes quite a substantial part of the total at very high correlation levels. It continues to be true that as default correlation increases, the total area covered by the two circles combined actually becomes smaller. A key point in understanding the insights that we will address next. We now introduce into the analysis two basket CLNs, a first to default and a second to default, whose size is $100 million each, and referring to our two reference entities above. The buyer of the FTD, first to default, receives a defaulted bond as soon as one reference entity experiences a credit event, and his note is then extinguished. The buyer of the STD, or second to default, receives a defaulted bond if the second reference entity also experiences a credit event, and her note is then extinguished as well. Until such time, each note holder receives a coupon fixed up front. It should be obvious that the FTD note holder will see his note extinguished if there is at least one credit event among the two reference entities. And it should also be obvious that the STD note holder will see her note extinguished only if both reference entities experience a credit event. Worksheet 2RE CLN adds rows at the bottom that calculate the default probability for each of the two CLNs. The FTD notes default probability is in row 12, and the STD's default probabilities are in row 13. Note that the numbers in these two rows are identical to the numbers in rows 11 and 7. For logical reasons. The FTD defaults if at least one reference entity defaults, while the STD, second to default CLN, defaults only if both reference entities default. Note importantly that for any level of default correlation, the sum of the default probabilities for the two notes in aggregate is 4%, a number also appearing at the very bottom of this screen in the Excel software, which is nothing more than the sum of the two individual reference entity default probabilities. So it should not be surprising that the second to default, STD, becomes riskier as correlation increases, which is consistent with intuition. As the basket becomes less diversified and therefore more concentrated, the likelihood of simultaneous defaults increases, and this is precisely the scenario that hurts the second to default. Less intuitive to many people is the fact that the first to default becomes apparently less risky if correlation increases. Yet this follows necessarily from our previous statement, since the sum of the default probabilities for these two nodes in aggregate is a constant 4% here. As the second to default becomes riskier and we move towards the right with higher correlations, the FTD must mathematically become less risky. We can use these insights also to price these two CLNs for any reference entity default probability and for any correlation level assumption. If we make one further simplifying assumption that the recovery value of a defaulted bond from either reference entity will be the same, we can proceed in effect to ignore recovery value as a factor in the pricing, at least on a relative valuation basis for the two CLNs, and we can then think about pricing them simply in proportion to their default probabilities, which are indicated in these two rows 12 and 13. The last two rows of the spreadsheet, rows 14 and 15, calculate what we have named the risk percentage for each CLN, which means the share of each CLN in the total default risk of the two CLNs combined. A proxy, so to speak, for relative riskiness. And this is calculated, as you can see, simply by dividing that particular CLN's default probability by the aggregate 4% default probability of the two CLNs combined, hence the D12 plus D13 in this formula. By now, you should not be surprised to see that when correlation reaches 100% and we are in the last column, the risk of the two CLNs becomes identical, each representing 50% of the total risk, so that the distinction in their labels between first to default and second to default has essentially become meaningless. To be slightly more accurate in our pricing approach, we recall the risk-neutral framework which we discussed in our earlier module, Pricing Default Swaps. And specifically, remember that the appropriate spread in that framework for assuming a credit risk equals the expected loss for the risk taker. Thus, we can add a few rows in various places of this worksheet to calculate for each reference entity and for each CLN the expected loss, and this will also become the spread under our risk-neutral framework. This worksheet, CLN pricing, shows the complete worksheet with the new rows that have been added at the bottom and the rows in which we previously calculated the scenario probabilities, now hidden essentially between rows 9 and 15. The spread for each reference entity in rows 7 and 8 is simply the expected loss of that reference entity, calculated as the product of its default probability times 1 minus the recovery value, as you can see through the function f2. And the same for the two credit-linked notes in rows 19 and 20. Returning to our earlier assumptions of a 2% default probability and a 40% recovery value, we note that the spreads under the two CLNs always add up in all cases, irrespective of the default correlation, to the same amount, namely 2.40%, as the sum of the spreads of the two individual reference entities. And this is entirely logical, since the CLNs in aggregate contain the exact same amount of credit risk as the two reference entities in aggregate, and since we have assumed consistently the same risk-neutral pricing approach throughout this worksheet. Note also that as correlation increases and we move further to the right in the worksheet, the spreads on the CLNs converge and eventually become identical when correlation is 100%. This worksheet and all those before can also be adapted for the case in which the two reference entities do not have identical default probabilities by simply changing this formula in cell C5 and making it independent of the input in cell C4. We go ahead and illustrate this on this next worksheet, CLN pricing 2, for the case where A's default probability is still 2%, while B's default probability is now 5%. Note that we have eliminated the last column showing the 100% default correlation case, since to our mind a 100% default correlation is logically and intuitively inconsistent with different spreads in a risk-neutral framework. After all, if those two entities have perfect default correlation, why would they trade at such a large spread differential? In reality, two reference entities can trade at different spreads, despite having a default correlation very close to 100%, due to some of the technical factors discussed in our module Pricing Default Swaps, such as a difference in liquidity or complexity or some such characteristic. You will note that the spreads for both CLNs here have risen from the previous worksheet, but by very different amounts. What used to be spreads that add up to only 2.4% now add up to 4.2%, and the great bulk of the increase in the spread on an absolute basis, not on a percentage or relative, but on an absolute basis, has gone to the first to default. The logic for this is that the increase in B's default probability to 5% has made the aggregate loss expectation higher, but this increase in B's default probability presents a far greater increase in risk for the FTD, which in a sense stands at the first line of battle, than for the STD, which is still quite remote and far away from the danger, as it were. The sum of these CLN spreads, as you can see at the very bottom of the slide through Excel, continues to equal the sum of the spreads, as we said a minute ago, of the two reference entities. Thus, these two numbers and these two numbers here continue to add up to the same if you look at each pair individually. But the impact on the first to default has been far greater, as we just said, in absolute terms than it has been on the second to default. This notion of how each CLN reacts to a change in default probabilities, or sometimes alternatively changes in spreads, is a critical one for the risk management of basket CLNs and will be addressed more formally in the next chapter. We note finally that you can also amend this worksheet a little further to allow for different recovery values for each separate reference entity. We will not do this here, but you can try your hand at it if you wish. We conclude this chapter, as we did the previous one, with a discussion of what rating a CLN referring to several credits might achieve. We saw earlier that for cases in which default correlation is low, close enough to zero, a reasonable approximation for the default probability of an FTD is to sum the default probabilities of the individual reference entities, provided in particular that we ignore the default probability of the issuer/SPV. Thinking about default probabilities will make this clear, just as it did in Chapter 1 when we examined the single name CLN. Assume, for example, that a 2% default probability over 5 years is consistent with a BBB credit rating, while a 10% default probability over that period is consistent only with a BB- rating. A first to default CLN referring to 5 reference entities with low default correlation to one another would therefore have a default probability equal roughly to the sum of the individual default probabilities of those reference entities, so somewhere around 10% in our case, or BB- as stated above. And if we keep adding more and more reference entities to the basket and continue to focus only on the FTD, first to default structure, the addition of default probabilities for each new reference entity keeps pushing the CLN's default probability further and further up, in principle, to the point at which its rating on day 1 could be the lowest credit rating that exists, above the status of default, i.e. the ubiquitous C from S&P and CA from Moody's. As we raise default correlations above 0 to any significant degree, we may no longer obtain a decent approximation for the note's default probability by simply adding together the individual default probabilities of the reference entities. But it would always be mathematically true, irrespective of the default correlation assumed, that each addition of a reference entity into the portfolio increases the CLN's default probability by some positive amount.